In the 1990s, the renowned physicist Marlin Scully from Texas A&M University suggested an experiment that demonstrated on the lab bench that one could change the past from the present. The experiment has been repeated many times since then, and is considered a prime example of a so-called delayed choice experiment. This astonishing experiment will be demonstrated here in a simplified form.
Yes, then let's take a look at what is set up here. This is the well-known Scully experiment, of course, in a simplified form here. But we want to demonstrate here what is actually measured in detail and what one actually sees. It must be said that a particle can behave like a wave or like a particle. So, the famous question, what is light? And ultimately, what is matter as well? This question has always intrigued physicists, and it was such that there was a problem. For example, there was a debate about whether light is a particle or consists of waves. Because there were experiments such as diffraction or sending light through a prism and so on, which typically only waves are capable of accomplishing. On the other hand, Einstein received the Nobel Prize for an effect he called the photoelectric effect. And this assumes that light has particle characteristics, because only this can explain how, for example, electrons can be ejected from selenium, like in the photovoltaic system on your roof, to allow electricity to flow at all. A lot of energy is needed for this, and only small particles have that. Yes, so in principle, the so-called dualism was born. People ask themselves, what is light really? Is it waves or is it particles? It is such that if one were to give the answer today, it is neither light and also all matter. This applies not only to light, we all consist of atoms, and the atoms in turn consist of atomic nuclei and electrons, and so on, small particles. And for these small particles, the same applies as for light. They have the same properties in this area. That means the question, are they waves or particles, was attempted to be answered. Quantum mechanics gives us an answer to this, namely the solution of the Schrödinger equation, which Ray talked about earlier, before one observes the particle, is essentially a quantum system, as it is called. And light is also a quantum system. One cannot imagine it because it cannot be observed. The moment one observes it, the Schrödinger wave solution collapses and the particle localizes at some fixed position. Then the property one wants to observe is destroyed, namely what the particle looks like without observing it. A lot of thought has been given to what can be done, but ultimately it has not been possible to explicitly observe a quantum system. One can describe it mathematically. This allows one to calculate properties that this quantum system has and that are also utilized, as Scully utilized in his experiment. But ultimately, it seems that matter and light are something. And depending on the apparatus used to measure it, this quantum system behaves as a wave. In the magnifying glass, light is enlarged, or it sometimes behaves as a particle when you want to generate electricity with it. Yes, so you have the problem that there is wave behavior and there is particle behavior. With wave behavior, you also have the well-known interference. You know that when you send light through a piece of metal with two slits in it, then it creates a pattern behind it, a pattern of light and dark stripes. You can explain it like this. If a water wave were to swim towards this slit, then two small water waves would form behind the slits and they would overlap. Then some wave crests add up and some wave crests come into wave troughs and thereby cancel each other out. When they cancel each other out, you have the dark spots. When they reinforce each other, you have the light spots. And in between, there is nothing. That is wave behavior. If you were to spray particles like a sandblast onto the two slits, then you wouldn't have this phenomenon. There are no interference stripes. There's simply a blob behind it, a spot with the sand particles on it. Depending on how large the slit is in relation to what is being sent through, it depends on whether I get interference or not. If the slits are small enough and the particles are small enough, then I get this interference pattern, which corresponds to wave behavior. Well, and what does all this have to do with us here? Now, let's imagine here on this laboratory table, there is a crystal sitting, and in front of it is an apparatus that generates a beam of light. For example, a laser light. You can even do it in such a way, there are photon cannons that shoot individual light particles at this crystal, like one particle every second. So you can slow it down and reduce it so much that you can essentially get down to individual light particles. Yes, and if you now send such a light particle to a specific crystal, then the crystal actually, as in wave theory, splits this one particle into two particles, and specifically into two particles of lower intensity. If you speak in terms of waves again, it would be like the wave is split and two smaller waves move apart in different directions. Now, it is such that these two particles, these two photons, the smaller ones, are called twin photons. And that's because they have a property that doesn't exist in larger particles, namely they are entangled. Entanglement is essentially the fact that two particles can somehow make contact with each other and are indistinguishable. Making contact means that if you change something in one particle, something changes instantly in the other. For example, if you observe it, then some physical property of the other particle also changes simultaneously. And this happens without any time delay. It doesn't matter where in the universe this occurs. A corresponding experiment was conducted on this. By Alain Aspect, this timeless influence of particles was explored there, experimentally proven. And now we have two such entangled particles. Entanglement is a kind of love relationship. They were once one entity, it was just one photon that went in. They are two particles that are divided, and they are still so intertwined in love that they have an agreement, which is, if possible, they want to reunite, no matter how and where. Now, this reunification is done here on the lab table. So when these two particles come out of the crystal in different directions, you can see that there are two mirrors set up that reflect these two particles in such a way that they meet again at a certain point. And at this point, where they meet again, we now place a semi-transparent mirror. You know semi-transparent mirrors, like those on sunglasses, where you can only see your reflection from the outside when standing in front of them. It's clear that it's only semi-transparent, otherwise the person looking from the inside wouldn't be able to see anything. So not all the light is reflected like with a regular mirror, instead part of it passes through. Now these mirrors can be adjusted so that half of the light passes through and the other half is reflected. You can imagine it a bit like having two ping pong balls that are now being reflected by the mirrors and hitting a perforated template. The holes vary in size and arrangement, done in such a way that half of the ping pong balls that hit it randomly encounter a hole, thus passing through, and the other half is reflected between two holes on the plate. If you imagine it this way, there are now four possible scenarios. We have two incoming particles, one from the right and one from the left. And now there are the four cases. Both can be reflected, the right one and the left one. They can both fly through a hole, or one particle can be reflected and the other can fly through the hole and vice versa. So we have four possible cases. And if you were to actually take ping pong balls and a hole template, this is exactly what would happen. At the back, there are two detectors that each capture the right and the left side where the particle arrives. And now if you have a 50% hole mask there, with 50% permeability exactly. Each of the four cases occurs with a probability of 25%. So if you send 100 balls through, you get on average 25 that are reflected on the right and left, 25 that go through both holes, and 25 where one is reflected and the other goes through, and another 25 the other way around. So those would be the classic cases. But with photons, it's not like that. And with very small particles, because this dualism applies there. And if we consider this wave property, as long as we do not observe this thing, the particles do the following through their mutual agreement that they have. Will they behave at this semi-transparent mirror in such a way that they are united afterward, becoming one flesh again, so to speak? That means there are not four cases here, but only two. And this is, of course, experimentally verifiable. One can conduct the experiment. Interference patterns, so to speak, are created, if you will. Although the individual particles are not a stream of particles over time, but simply just two pieces, but a unit of time. But it is just that the love agreement ensures that always either one particle, for example, the right one, is reflected, then the left particle goes through a hole. Or vice versa, if the left one is reflected, then the right one goes through a hole. The two other cases, where both are reflected and then not united, or where both simultaneously fly through a hole and are also not united, do not exist in the experiments. That's just how it is. That also describes quantum mechanics. It predicts it to be so. So that's still nothing special. That's just how it is. It can be measured. It can be mathematically described. Now, why and how and what exactly the love speech looks like, well, who really knows? But it is an experiment that can be done. So now Marlin Scully was interested in which of the two particles took which path before the reunification. So you don't see it afterwards. At the detectors, two are always united again. You can reconstruct it, which path each of the particles took. Well, the idea was from Marlin Scully, you simply place a marker in the path of one of the two particles somehow. And this happens with so-called polarization filters. These are filters that rotate the plane of oscillation of light, but otherwise have no influence on this measurement process. But the particle is thus virtually marked. With small ping-pong balls, it would be like dabbing a spot of paint on one of the two balls while it's on its way so that it's recognizable where it is. Well, interestingly, due to this marking, the Love agreement suddenly no longer applies. The wave behavior disappears, and the things behave like ordinary grains of sand or ping-pong balls that you send through. So if one photon is marked, then suddenly all four classical cases come up again at the detectors. So there are not only reunited photons, but there are actually also individual ones. Of course, there are still reunited ones, half of the cases, and the other 2 times 25% are the other cases that also occur in the classical scenario. So that's just how it is. You can't change it. But what is interesting now is the following. Scully considered if he now places behind this whole mask, behind this semi-transparent mirror, in front of both detectors, builds an apparatus, namely a second polarization filter, which is a polarizer, cancels out, but the other photon which is not marked is not affected. That means if a photon is marked by the polarization filter beforehand, then this marking is erased. That's why it's called the quantum eraser. Quantum eraser. It is erased if it was not marked at all. If it was the other photon which was not marked, nothing happens. It remains as it is. If you will, it's a kind of washing machine that stands in front of the detectors, washing out any potential stains from this ping-pong ball. If there were none, it remains as it was, and if there was one, it is gone. Yes, the trick now with the whole thing is that I can now move this detector far away from the mirror. And also this washing machine, this eraser, this remover can be placed in such a way that I can decide whether to turn the eraser on or off after the photons have already passed through the aperture. That means just before the detectors, I pretend with free will to decide, now I turn on the washing machine, so that any stains are removed, or I decide not to turn it on and it remains as it is. I can make this decision at a time when the particles have already passed through this semi-transparent mirror. That's why it's called delayed choice. So I wait with my choice until the particle has already passed through this aperture mask. So what comes out now is astonishing. If I turn on the washing machine after the particles have already passed through this aperture mask, then the reunification agreement takes effect, meaning I only get the two wave cases again, so to speak, the reunited cases, where the two particles are reunited at the detectors. If I don't do it, if I don't turn on the washing machine, then I have the four smooth cases, as mentioned. And the problem now is, how do the two particles know when they arrive at this semi-transparent mirror there that I later, at a later time, decide by free will to turn the washing machine on or off? How do they know that? Because since that happens later in time, they would have to know beforehand how I will decide later. Yes, because the agreement is we always stay together if you fly through a hole. I remain reflected if I pass through the hole, you reflect. This decision of the particles, so to speak, is made at the mirror. But if I turn on the washing machine afterwards, then suddenly there are only reunited photons again. That means either the photons can see clearly, knowing beforehand at the semi-transparent wall what I intend to do later, or the interpretation is that my action, namely turning the washing machine on and off, using or not using this quantum eraser influence backward in time of the behavior of the two particles at this semi-transparent mirror. That is one possible interpretation. In any case, it is technically feasible to measure this. One can measure it. Scully has even devised and conducted experiments where this decision, whether to use the quantum eraser or not, is made days later when the things have long since arrived at the detectors. But one must not have looked at the detectors beforehand, so to speak, because then it's too late. The decision has been made. But if I decide afterward, retroactively, when I say I have now activated the quantum eraser, then they arrive like that, the particles where they were already measured yesterday or the day before, that it is so. That means mystery upon mystery, but it seems possible to influence something from the present into the past, at least with entangled particles. To what extent this can be used in practice for time travel or something like that, or for altering one's own past, that remains to be seen. They would have had to be entangled with their duplicate to change anything, whatever that may be. In any case, it is something that apparently is the way it is. And it is not just limited to this small laboratory table here, but it can even be conducted on a cosmic scale. Because fortunately, there are so-called quasars. These are stars that emit light in many directions. A star from me like a candle, and in between lies a large Milky Way. One could actually not observe the quasar at all. But around it, the light is guided. This gravitational lens, as it is called, is essentially the effect. A large Milky Way acts like a big lens, but so that the light rays come around from above and below. And now on Earth, one can conduct an experiment in such a way that the behavior is similar to what we have here, but in reverse in time. So it is that the light rays around this gravitational lens behave once as waves and once as particles, meaning they either pass through both simultaneously or alternate between above and below. And this behavior is naturally even more astonishing because the light rays go back millions in time. Long before there was an Earth, they had already passed through this Milky Way system, this galaxy. That means I can virtually influence through an experiment today how light traveled over a galaxy millions of years ago. From a measurement perspective, it seems to be the case. One could even conduct two experiments simultaneously. One is set up so that the light must go around above and below, the other so that it goes simultaneously. And then the question is, what really happened in the past? Hugh Everett has a solution for this. He says there is a many worlds theory, which states that whenever you make a decision whether to turn a washing machine on or off, the universe virtually splits. It duplicates itself. But there are different pasts. For example, there is precisely one past. There, the two particles have united, and at the same time, there is a parallel universe. There, the particles have not united. And which one you slip into now depends on how you decide. You virtually always slip into the fitting past. For your washing machine from the self-switching, but the other worlds are just as real, according to Hugh Everett. A bit unsatisfying because it is very speculative. And ultimately everything you do, if you decide today not to commit a mod, splits the universe, and in another universe you have committed that mod. So it would practically not matter how you decide, there is still a universe where you can decide differently. Of course, this is very speculative and not really believed by physicists, this model. It comes from the 1950s of the last century, but it is an explanation. It is a theory that somehow fits the facts.
Now we want to briefly see a conclusion. Why has the question of whether space and time exist become questionable as a result? Well, Nobel laureate Alan Asperg has experimentally shown that different particles behave as if there is no space between them, as they act like a single object, even when billions of kilometers apart. They exchange information without any loss of time, or rather, they behave as if they were just a single particle. The old assumption that there could be hidden variables connecting both objects has also been experimentally disproven. Keyword, Bell's inequality. So much for space, now on to time. Marlon Scully was able to demonstrate in the experiment shown here that the particles also behave this way over time, as if they were just a single object extending from the past into the future. This seems to suggest that the phenomenon of time is merely a perception arising in the observer, but actually possesses no reality. Another note on the frequently arising question of whether quantum physics disproves causality. The answer to that depends on how the definition of the law of causality is chosen. There are several of these. The general version states that everything that comes into existence has a cause. Mind you, not everything that exists has a cause, but only everything that comes into existence has a cause. This law is not violated by quantum physics either. If this law is restricted in the way it is often done in physics, namely, that the same causes always have the same effects, then this law is clearly violated by quantum physics. There seems to be genuine randomness. Nevertheless, the general version of the law of causality is not violated. because every random event that comes into existence has at least one cause, namely the random generator. However, the effects are not always the same, even with the same cause. However, with quantum mechanics, one can specify the set of all possible effects from which one randomly emerges, along with their probability of occurrence. A temporal connection to causality is also violated. While normally the cause comes first, followed by the effect in time, Alan Aspect was able to demonstrate through his experiments that a cause arises absolutely simultaneously with its effect, even over arbitrarily large spatial distances. The Galli experiment finally shows that a cause can also occur after the effect, like the switching on and off of the quantum eraser. This is the cause occurring after the effect in time, namely, the behavior of the recombination at the semi-transparent mirror. Thus the effect is impressively demonstrated. Here the cause is therefore after the effect in time. So with quantum physics, one does not have to abandon the law of causality, but only the uniqueness of effect to the same cause and the temporal order of cause and effect. The law of causality thus becomes a space and time-independent meta-principle. How does it continue? In the USA, an entanglement and thus an exchange of information between particles that have already been destroyed, so to speak, are dead, and particles that do not yet exist, that is, are only created later, has been experimentally conducted. All this shows that our concept of space and time probably has little to do with reality out there. Some physicists therefore believe that what is out there only comes into existence through our observation, which seems to be confirmed by further quantum physical experiments.
So I hope this has given you something to think about, and I thank you for your attention.
Is more than just a game, we'll never be the same, and all the love you gave I remember and long for more than joy and fame. Just one thing was my aim, it's more than I could claim, it's alive with you. I sing this song for you, for everyone I knew, for times when I felt blue and you stood with me. I prize the time you spent, I wish there was no end to all the things we've done, but life is going on. Treasure is not small that I carry in my heart. So I say goodbye to you. We all can start anew. The world goes on to turn and we're turning. That's all the time we have. I hope you are not sad. I wish you all the best, and that you are always best.